In comparison to the ordinary satellite, CubeSats are quite inexpensive. CubeSats will cost around $40,000, while a satellite will range from $50 million to $500 million.
Arduino, an open-source prototyping platform, originated at Every Interaction Design Institute and was used for fast prototyping. Now Arduino boards can read inputs and perform the outputs quickly.
Arizona State University, or ASU, will be making a CubeSat that is going to characterize the water content of the South Pole of the Moon. In addition, soon there is going to be 2 CubeSat twins that are going to be sent near Mars along with the next Mars rover.
Our group divided up into 3 sets of partners to make CubeSat designs on Autodesk Inventor, which is a computer software program that is used to design 3D structures. The CubeSat Kira and I made, CubeSat 1, has legs on 2 sides with a plus and an X design, and is recessed for solar panels to be attached to all sides except for one.
We decided to put holes in our CubeSat, CubeSat 1, so that the wires attached to the solar panels could easily get to the inside material.
The design Mateo and I developed, CubeSat 2, is an X shape with a circle in the middle because we wanted ours to be similar to the one we saw while brainstorming.
We decided to put a flat side on our CubeSat so that it would not be floating when it printed.
The design Isha and I made, CubeSat 3, has an X design in it to make 4 triangles, which are the most stable geometric shape.
We did not have a flat side because we decided the door would be a flat side, and this way would get more power because then we could put on more solar panels.
We combined our 3 CubeSat ideas for our new design. It has an X design on all sides but the door because that forms triangles, which are a simple yet stable design.
It is recessed on the 4 outer sides to mount solar panels to give it some space from them being damaged or scratched. It also has legs to protect the door when it swings out.
One of the X sides is recessed on the inside, so we have one flat side to print on to avoid printing in midair. The X over the solar panel decreases power some because less sunlight can get to it, but it is only on one side and is necessary for additive manufacturing or 3D printing.
One of our sides broke off because it was too thin. We also had no room for the hinges to rest on for when we attached the door to the CubeSat.
After we finished making the basic design of our CubeSat, we used Fisher Technic parts to open our door. These parts are like advanced Legos, but they work with code. We used RoboPro, a programming software, with the Fisher Technic parts to open the door of our CubeSat. This is a video of how it opened.
The program begins by waiting for an input, which is a switch, then opens the door by running a rack and pinion for 3.1 seconds, and then turning on the lights for visibility and making observations. After the switch is pressed again, the rack and pinion retracts, which closes the door.
The new CubeSat printed at a lower travel speed from 90 millimeters per second to 50 millimeters per second, and the extruder temperature was risen from 215 degrees Celsius to 225 degrees Celsius to make it more solid. New CubeSat's design has thicker sides and more room for hinges on the inside.
The next step of the project was to find a way to open the door in space without Fisher Technic parts because they have to be connected to the computer. We decided to do research on Arduino boards and servo motors to understand how they would work in our CubeSat since we could download our programs to them.
We found that we could get an Arduino kit with projects to do that. We also needed to push the door open.
We cut out rectangles of foam board and mounted them onto the CubeSat to represent the solar panels. There are cutouts within the foam to fit the X's so that they have a better chance of staying on. In theory, the solar panels will supply extra power in space.
To supply our 9-volt battery to power the Arduino with solar panels, we found that we could use the 46% efficiency solar panels by Soitec and Fraunhofer because they are the most efficient type of solar panel and are used by the National Aeronautics and Space Administration, or NASA, in space.
The surface area of our solar panels on the CubeSat were 5,625 millimeters squared. So if we use the solar panels, we would get 2.25% of the solar insolation when it is measured in watts per meter squared per day. We found this by taking the 46% efficiency, the size of our solar panels, and the number of our solar panels. After this, we practiced using Arduino by doing projects to come to our overall goal of opening our CubeSat's door.
Some examples of projects we did were the levometer and the mood cue. The levometer measures your body temperature to say how hot you are. The code worked by testing the temperature of the user's hand when they place their hands on a heat sensor.
We programmed it so that every time the sensor picks up heat 4 more degrees Celsius than the base temperature, another one of the 3 LEDs turns on. So when the hand was at least 12 degrees more than the base temperature, all of the lights were on.
Another project we did was mood cue, which had a servo motor and spun 180 degrees, stopped, and went back 180 degrees. The code started by connecting the potentiometer to the servo motor. It tracked the position of the potentiometer and replicated it to the motor, hence making it turn.
We opened the CubeSat by using a servo motor, the Arduino, and balsa wood. We attached the servo motor to the side of the CubeSat so when the code started, it would move and lift the door up.
A problem we had was we could not get the servo to work with the Arduino. Members from another group told us that we had wired it wrong. The new way worked, but there was another complication. The servo would not move.
It was broken, so we had to think of something to do. First, we debated buying a new one or getting another group's. We ended up using another group's servo while they were not using it.
To assist the servo motor, we used balsa wood, which is a very light wood. We used the balsa wood to build a stand to hold the servo motor in place as it pushed the door open.
We also used a separate piece of balsa wood to extend the servo motor's propeller to push the door further.
After this, we decided to print yet another CubeSat.
We made this CubeSat have a stand put inside it and attached to the walls to make it more stable and clean.
The balsa would use zip ties to attach, which still allowed movements but aren't as reliable. But this CubeSat had a few problems, one of which was that the stand was too tall for the servo. Another was that our door wouldn't fit on the CubeSat.
We learned that the first 2 CubeSats were printed 10 millimeters too short and the blue one printed correctly. We based our measurements of the stand on the red one, thinking they'd be the same size, which made the door too small for the blue CubeSat.
So we made the decision to go back to the red CubeSat.
It took a lot of work and research to finish the CubeSat, but it was worth it to see how nice everything turned out. Thank you all for listening.
Not being very code savvy myself, I really appreciate your little overviews of the code that you used. You didn't get into too much detail, but it kind of gave me an understanding how it processed.
So you said the red was too small. Can you explain that a little further?
Well, we didn't measure it after we 3D printed it. So when we 3D printed the blue one, it actually was the right dimensions from Autodesk Inventor, and we didn't know that ours before were too small, and so we just made the idea that the blue one was too big. But then when we measured it, we realized that it was the exact measurements, and our other ones were too small for it.
And too small in what way?
Like, I think they were 5
in every
millimeters.
way, like what it was is on the red and the black one. They both. We actually went over the locking system. They were both 105 millimeters tall on Inventor, but when it printed, they ended up being 95. So it printed 10 millimeters too small, and we never realized. So then, when we based the measurements of the stand and the door, then we tried to use the same door, and with the stand inside of the CubeSat, it had messed up the measurements so that it did not work.
So what drove the decision to go back to the red cube as opposed to try to fix and get the maximum volume that you were allowed?
Because we had 2 days left.
Yeah.
Fair enough.
You had mentioned you only put the solar panels on the 4 sides, and you said you needed the flat surface on the bottom. Did you think through what the ramifications were by not having a solar panel on that bottom side? If you're in orbit, do you think that might be become a problem?
We didn't really think of that.
Yeah. And that's one thing as you go forward, and I mentioned it with one of the earlier groups, you want to put as many solar panels on that CubeSat as you can, because you can never have too much power. And on that, it's something that you need to go back and think through and rethink how you could stay within your dimensional allowances, but yet still have a solar panel on that fifth side. So it'll be real important when you're on orbit and you have no idea which way is pointing to the sun.
One reason we made that flat side is because with this one, the bottom, well, with every CubeSat we made the bottom flat because we didn't want it printing in midair, because that would make it very thin, and it would look like the bottom of the servo stand. If you look in that, looks all stringy.
Yeah.
Yeah.
I noticed on your demo, and I don't think the other teams have this, she had sort of a tape temporary hinge on your door. If you were going to continue with this design process, would you put in an actual hinge, or would you have the door pop off?
We would probably put in an actual hinge, because if you could take the door off and remove the tape, then you would see like this flat. I'll just show you this before I take it off. This is. We have this flat side right here for hinges. You guys want to look at that? One side you can see it's completely cut off.
Do you think having an actual hinge would give you some advantages?
Yes, less space debris. If like you made maybe 50 CubeSats with the same design with hinges in it, that would be 50 less CubeSat doors floating around.
Yeah. Orbital debris is becoming a real problem.
So what are, as you say, this first attempt or third attempt or however many attempts, what do you guys think are you've got a base set of what you designed to, what do you guys think is the next things you would add to make this more suitable for something that would launch? What improvements would you make based on your experiences?
Probably add a solar panel to the bottom, so we have the solar panels, and we most likely make the stand smaller so we can actually put the servo on it without the zip ties.
I have a question for y'all, and maybe for the entire group. Did you ever weigh your final CubeSat?
No.
I'm just curious, because I know a lot of CubeSats, one of the big problems they have, or one of the big design constraints we have is they can't be too heavy. You can't send up a big brick up there and call it a CubeSat. That's too much. It's going to cost a lot more money too. So knowing how much it weighs and how it's going to behave in space is really important too. So for the other line, maybe getting a weight measurement would be a really good thing to know. It'd be a very good thing for the presentation. Cool.
That's a good point, because a lot of our design challenges are getting an optimal design that meets our requirements within our constraints. So we typically have mass constraints, body constraints. You got to look at the volume very closely, but mass is one that all of our projects have to struggle with.
So one thing that we had a lot of trouble with is finding costs. There was a broad range of, this is what a satellite costs, this is what a CubeSat costs in space. We looked at dates to see, because things go up. Sometimes they go down in price depending on the technology, but we couldn't really find, we tried, but we couldn't. Y'all run into that very often? I don't think you really have to worry about that.
No, they're happy to tell us how much. They're happy to send us a bill, I'm sure.
Well, you know what
Yeah.
did we sound, I saw you kind of, when they gave a number once, I saw you kind of think about it, and I'm wondering, were we off?
Well, I was going to ask, and I'm asking all the kids here, why do you think CubeSats are cheaper? Every one of you said $40,000. Why is that?
They're smaller.
Because they're smaller and
And they are in the leftover space in the rocket.
That's
Yeah,
a secondary
they
payload.
require less technology than other satellites. Don't use as many materials.
Well, let me ask you that one. You say they require less technology, but can you do more expensive technology, better science and things with CubeSats, and then offset all this spacecraft cost? Does it have to be lower level technology, or can you do higher level?
It's not lower level
Higher,
technology, it's
higher.
just
It's
less.
less.
Yeah.
Less.
So you're not using as much like boards or programming as you would in a rocket.
Okay.
So I think it was hit on. I think you mentioned, but CubeSats are cheaper because you can extend the cost of the launch across several other payloads, right? Because it's tiny, and you're not going to have a dedicated flight for just this. If you are, you have more money than sense. Because that vehicle is what costs. That launch is what costs. You're looking at the cheapest launches to get something out to LEO are around $40 million. I don't even know if we can do that anymore, Kim. It's probably 56 to 60 is probably. So that's a fixed cost. And what we mean by that is you're going to have to pay that regardless. You can't negotiate that. When you go in and start the product, you know if I'm going to put something in the air, it's going to cost me $60 million from the start. But what you're able to get away from, which I think one of y'all mentioned, is there's other people who are going to put costs on there. So you can share the cost on multiple payloads. So the CubeSat is not cheaper because it has less technology or material, because the most costly aspect of most of the things we put up is the launch vehicle itself. And so if you can share that cost and get in somebody's trunk, not have to pay for the car, then that's a really good thing.
I think we read about that.
No, I would say not to think of them as low technology efforts. The two we're working on would argue that are actually tech demos. We're demonstrating new technology with CubeSats. And getting it smaller doesn't mean you have to do less science. It just means you do different science.
Sometimes making things small is more of a design challenge, because you have to do all the same things in a very small, very concise and efficient manner.
Yeah, so don't think CubeSats can't do science. There's a lot of them that do. National Science Foundation funds a lot of them.
There is go ahead, sorry.
I was going to say, talking about, it's kind of hard to get information on cost. Well, two of the CubeSats that we're developing or co-developing for the first launch of SLS, we're sharing the same bus. So we have different signs, different propulsion, but we're going to design the bus once. We're partnered with JPL. So that's a way to kind of cut the cost overall for both projects. So we're always trying to find ways to leverage off of other activities. And so that's why I think it's kind of hard to find a really clean cost for a CubeSat.
Yeah, and that ride that Kevin's talking about, if you really look at the cost of that first launch, I mean, and you had to pay for that, it's got to be close to $1 billion. So just trying to learn, put that new technology in place. So needless to say, putting that on there, if you had to pay for the ride, doesn't make any sense.
We thought, and I know that the kids think this because we talked about it, we thought that the CubeSat was a great opportunity for people who don't have millions of dollars. So we think it's a great thing. You know, we do. We think it's something that I definitely, you know, hopefully Dr. Hall and I, we're going to come up with a new plan for next year, and we're just going to switch back and forth. We don't want to leave the CubeSat. So these groups will go away every 2 years, we said to 8th grade. And so it's, we think it's a great thing. I mean, you're sharing payload, you're basically being more efficient about things. And yeah, you're sharing, but you're still allowing college professors that want to send something up, or somebody wants to send something up, a way to do it in a reasonable amount of money. So there's nothing bad about that.
I think you're absolutely right. And I did not work this directly, so don't quote me, but one of the CubeSats that were going to fly on the first mission, they chose by a competition called Centennial Challenge, run out of headquarters. And one of the finalists was developed by a high school group. And it's for a 6-gig CubeSat that I don't think that made the final cut, unfortunately. But I mean, it's an awesome opportunity for colleges and high schools to actually be able to fly something.
Any more questions? I want to ask you guys the same question. What was your favorite part of the whole process? Or least favorite?
Designing in the CubeSat and then printing it and making all the
Yeah.
foam board solar panels.
Okay. And how far are y'all along in math at this point?
We're all in different math classes.
Okay.
Differential equations.
Yeah, calculus, that kind of thing yet? Y'all can
I
handle
think
that.
Nolan might be the
Yeah.
highest.
Yeah.
I think Nolan's the highest in geometry. So.
Well, I'll just say the big part of engineering, y'all probably already know this, is the mathematics part of it. So if you have any desire to be an engineer, even if you don't like it, it leads to the hands-on stuff, and you don't necessarily have to do it every day once you're done with your engineering degree. But you got to focus on it early on to get through and get all the engineering physics. Just words of encouragement for what your interests are, where to lead you. You guys are way ahead of anywhere I was at your age. I was watching cartoons and playing Game Boy. So you guys.
We do that on Tuesdays.
That's Tuesday? Okay, that was every day for me.
They still have Game Boys now.
What's this? It's the
3D or something?
I had the pocket. It wasn't even colored. But anyway, all that to say is, like, you guys are so far ahead of where I was. Y'all are gonna write your own futures.
I've got the color.
You've got the nice.
Thank you.